first PPT. And if you see the definition we have seen in that one, what is the point to be noted there? And we have seen that whenever you have that multiplication, when it should be multiplied, if you see the note there, please note. So in that note, if you see the and stands for into, that into is nothing but multiplication, and multiplication is taken for intersection, and or stands for plus, and that plus stands for union. That is a summary of the previous definition. Okay, now let us today see the permutation. What is the permutation? Let's go to the 6th slide. Just wait, previous slide. So in the doubts of last class, and yesterday one girl asked about this, sum of all odd digit numbers formed by taking the given n digits including 0. I will explain it in the middle, and just for the sake of the introductory part, I'm giving you this. Let us discuss the formula after 15 minutes. Okay, now let us start with this one. Well, the permutation, the dictionary meaning of this, it is nothing but the arrangement. Arrangement of what? Arrangement of things or objects or whatever it is. And if you arrange the things or objects by taking some means SOME, some or all at a time, is nothing but a permutation. So if you see like ABCD, if you take 2 letters at a time, and if you arrange them, 2 letters can be written like this, AB, and AB can be written as BA. This is AC, can be written as CA. This is AD, can be written as DA. This is BC, can be written as CB. This is BD, can be written as DB, and this is CD, can be written as DC. Now these many different arrangements we can make by taking 2 at a time from ABCD. Similarly, if you take 1, 2, 3, 4. 1, 2, 3, 4. How many 2-digit numbers that can be formed using 1, 2, 3, 4? You can understand it is 1, 2, 2, 1, 1, 3, 3, 1, 1, 4, 4, 1, 2, 3, 3, 2, 2, 4, 4, 2, 3, 4, 4, 3, like this. So you can see the different number of arrangements that can be done. So what is the important thing to be noted in a permutation arrangement? In the permutation, whenever you are choosing 2 things, AB, here also 1, 2, here like 3, 4, whenever you are choosing the things, the order of things is also to be taken into consideration for a permutation. So the permutation involves in the consideration of order of things also. So the important thing to be noted in a permutation is order of things is to be considered. Should not forget it. Very important point, because later in the combination we will see the difference between a permutation and combination basing on this only. So wherever the order of things is to be considered, therever you have to apply a permutation. So here AB is written as BA. Here 1, 2 is written as 2, 1. 2, 3 is written as 3, 2. Clearly in this case, of course, the numerical value differs, because it is 23, it is 32. There is numerical value differs. So in this case, definitely whenever you come across the arrangement of digits, unless and until it is specified, you have to consider the order of things also in case of the arrangement of digits. But if you see this one, it is clear that 12 different from 21, 13 different from 31, and 14 different from 41, 34 different from 43, and you can clearly understand this. But this can also be questioned like this: how many 2-digit numbers that can be formed from 1, 2, 3, 4? How many two distant numbers that can be formed from 1, 2, 3, 4, in which the digits are present in the increasing order of magnitude. The digits are present in increasing order of magnitude. Then what happens? 1, 2 we need. We don't need 2, 1. 1, 3 we need because it is an increasing order of magnitude. We don't need 3, 1. 1, 4 we need. 4, 1 not needed. 2, 3 we need. 3, 2 not needed. 2, 4, 4, 2 not needed. 3, 4 needed, but 4, 3 not needed. So the same question can be altered by not considering the order of the things. So understand, wherever we will discuss it in the combinations again. So what is the primary thing that is to be observed in a permutation? The order of things is always to be considered after choosing the things. Like AB taken, immediately it is rearranged as BA. Wherever it is not necessary, like 1, 2 is not to be written as 2, 1, according to the question you have to proceed. So for this permutation, now we are going to derive the formula for NPR. NPR can also be written as P of N comma R. NPR can also be written as P of N comma R. What does it mean? Permutation of N things, N dissimilar things by taking R at a time. Permutation of N dissimilar things by taking R at a time. It can be denoted like this and it can also be written like this. So, and its formula we're going to derive now, that is, we have seen yesterday in the principle of counting, whenever we are making the operations, we have considered the operations as different boxes or different blank places, and we have filled these blank places with different operations, and we have derived the final answer. Similarly, in this case also, you have N things in your hand and R things are to be taken. As we have seen ABCD, in ABCD we have taken AB, BA. How many things are taken? 2 things are taken. So this is here N is 4. N is 4 and R is 2. Like that. So in each of the arrangement, how many blank places do you have? In each of the arrangement, you have 2 blank places. Similarly, for N things, R things are to be taken. Then R things, for R things, how many blank places will be there? And you will have R blank places. This is first. This is second, this is third, this is R minus 1th, and this is Rth blank place. Now, let us see. First blank place can be filled with N things in how many different ways? First thing can be written, second thing can be written, third thing can be written, and so on. Nth thing can be written. Okay, now one thing is already filled. Understand, this is permutation stands for without repetition. With repetition, what will it be? We will see. Without repetition. Understand it, please. Without repetition. So, N things can be filled in the first blank place in N different ways. Because one thing is already filled, there will be remaining only N minus 1 things. And for the third blank place, there will be remaining only N minus 2 things. And so on. You can see if it is 3, it is 2. If it is 2, it is 1. If it is R minus 1, it will be N minus of R minus 2. That is N minus R plus 2. And it will be N minus of R minus 1, which will be N minus R plus 1. So here also, it is simply based on principle of counting. That's what you have to understand. What is the principle of counting? First operation can be performed in different ways. Second operation can be performed in N minus 1 different ways. Third operation can be performed in N minus 2 different ways. And so on. Rth operation can be performed in N minus of R plus 1 different ways. So all these operations, one after the other or simultaneously, can be performed in N into N minus 1 and N minus 2, so on into N minus R plus 1 different ways. So you have to multiply this because these are all to be performed simultaneously or one after the other. Now, for the sake of convenience, what we do, you can observe that these are in the each term is reduced by 1. That is, these are in the descending order. So what we do, we want to make it a factorial. You know the meaning of factorial. So we will multiply this this total product with the next term. The next term to this is n minus r, that is minus 1. And next term to this is n minus r minus 1. And so on. To complete the factorial, we multiply with this term and we divide with the same term. It is just to complete the factorial. Now, if you read the numerator, it is 1 into 2 into 3 into so on into n minus 2 into n minus 1 into n, which is nothing but n factorial. Which is nothing but n factorial. Now, if you see this one, 1, 2, 3, so on, n minus r. It is also the product, and you can understand it is a consecutive product of n minus r numbers. It is nothing but n factorial by n minus r factorial. So, understand the formula for a permutation NPR is nothing but n factorial upon n minus r factorial. For our convenience, using the principle of counting, we have derived the formula for NPR as n factorial upon n minus r factorial. This is, understand, without repetition, please. This is without repetition, So, without repetition, n factorial by n minus r factorial, then what should it be with repetition? You can clearly understand, because without repetition, the thing used here should not be used in the second blank place. The thing used here should not be used in the third blank place. The thing used here should not be used in the later blank places. So, that's what you have to understand. So, if the repetition is allowed, what happens? If the repetition is allowed, first blank place can be filled in n different ways. Second also can be filled in n different ways. Third also can be filled in n different ways. All become n only. Then thereby this becomes n, and this also becomes n. This also becomes n, and so on. All the blank places can be filled in how many different ways? N into so on into n into n. How many n's are there? R n's are there. So it is nothing but n per r. So what is the conclusion here? What is the conclusion here? It is that nothing but without repetition, NPR is nothing but n factorial upon n minus r factorial. With repetition, it is n power r. So let us write the final formula. Just I have derived this to explain you that this is also based on principle of counting. So, number of permutations without repetition is nothing but NPR. It is also denoted as P of n comma r. And the formula we have just now derived is n factorial upon n minus r factorial. Number of permutations now with repetition is equal to n power r. So understand the difference here with repetition and without repetition. So that's what you can see in the first slide, that is derivation of P of n comma r n factorial upon n minus r factorial. That's what just now I derived it. Arrangements with repetition also, it is n power r. Okay. So next is the number of permutations of n dissimilar things taken not more than r at a time, when each thing may occur any number of times, is n into n power r minus 1 upon n minus 1. What does it mean? Just to go through the definition once, just to go through the statement once, rather I can say. The statement here is the number of permutations of n dissimilar things. All the things should be dissimilar. Then you may think, the things are not dissimilar, what should it be? We are coming to that next. So if n things are dissimilar things taken not more than r at a time, not more than r at a time means you can take one thing, or you can take two things, or you can take three things, or you can take four things, and so on. You have to take maximum of r things, and always remember n is greater than r, of course. Okay. Now if one thing is taken, it is n power 1. If two things are taken with repetition, n square. Just now we have seen the formula, it is n power r. With repetition, n square, plus three things are taken, it is n cube, and so on. R things are taken, it is n power r. Now if you take n common, it is 1 plus n square plus so on plus n power r minus 1. You can clearly see that it is a geometric progression. Sum of n terms of GP is nothing but n power r minus 1 upon n minus 1. So, the number of permutations of n dissimilar things taken not more than r at a time. What does it mean? Not more than r at a time means in this case we have taken only 1. In this case we have taken 2. In this case we have taken 3. In this case we have taken r, maximum of r. So, the sum of all these will give you n into n power r minus 1 upon n minus 1. This is sum to n terms of GP. So, you understand that. So, now how many number of functions and others can be defined using this? This is an important thing to be understood. But before that, you must know the definition of a function. Simply, I'll tell you like this. F maps A to B. What is A? You know, A is the domain. What is B? B is the codomain. Okay. Now, the domain is consisting of, let me say, 3 elements, and the codomain is consisting of, let me say, some 5 elements. This is A, this is B, and the mapping F. Let me say, if F is to be a function, then what is the rule to be followed? Then you will better understand a function if you understand what is not a function. What is not a function? If any element of domain, if any element of domain is without association to the set B, then it is not a function. It is not a function. So understand, every element of domain must have exactly one and only one association with the set B, and this is not a function. That's what I'm explaining. It is not a function. If any element is left without association, then it is not a function. Then it is like this, and it is like this. If any element of domain has more than one association, then also it is not a function. These are the two things you have to remember. You have to remember what is not a function. If any element of domain has more than one association, then it is not a function. If any element is left without association, then also it is not a function. Now, our interest in permutation, using permutation, can we write the number of functions? If F is defined to be a function, can we write the number of functions? Okay. Now, according to the definition of the function, let A and B be two non-empty sets. Let A and B be two non-empty sets. And to every element of set A, exactly one and only one element of set B is associated, then F is said to be a function. This is a better example is if you take your classroom and let us suppose there are totally 30 students in your classroom, and on that day only 25 students are present and 5 students are absent. Then if your teacher comes and calls everybody's name from the attendance register, let us suppose that it as a set A, and if your teacher is calling the attendance, then 5 students will not have any association because they are absent to the class. Then it is not a function. It's not a function. Unlike that, if the teacher comes and he or she is asking your name and she is marking here, that means the number of students present in the class is taken to be set A, and set B is the attendance register in her hand or in his hand. Then set A to set B will be definitely a function, because everybody in the class will have a unique roll number, and everybody will be associated with the attendance register. So that is a simple example for a function. So now here we are interested to know how many functions that can be formed in this case. Now, x1 can be associated to any one of these 5. That means x1 has how many chances here? 1, 2, 3, 4, 5. So x1 can be associated to any one of 5. So x1 has 5 chances. And similarly, x2 has also 5 chances, and x3 also has 5 chances to be associated. So first operation 5, second operation 5, third operation 5. So it is nothing but 5 into 5 into 5. It is 5 cube. In what way this can be related to this? This is 5 is nothing but n of b. It is number of elements in set B. And 3 can be said as n of a. So n of b whole power n of a. N of b whole power n of a is nothing but the number of functions. You might have understood this now, how we derived this using simply the principle of counting. So the number of functions to be concluded here, the number of functions, what are the number of functions here? Number of functions, total number of functions, I can say, total number of functions. For f maps a to b is n of b whole power n of a. Understand it, please. N of b whole power n of a. That's good. Now, this is total number of functions, and you know the 1-1 function. What is a 1-1 function? 1-1 function, f maps a to b is said to be 1-1 function if to every element of set A, exactly one and only one element of set B is associated. Just now we have taken the example. That is a 1-1 function. What is it? The number of students present in the class is set A and the attendance register is set B. Then if you map the number of students present in the class to the attendance register, then it is nothing but a 1-1 function, because no student in the class will have 2 roll numbers. No student in the class will have 2 roll numbers. That is, everybody will have unique roll number. That is why that is nothing but a 1-1 function. So number of 1-1 functions means if you take this one, the same example, x1, x2, x3, and y1, y2, y3, y4, y5, x1 map it to x3, x2 map it to y1, and x3 map to y5. Is it a 1-1 function or not? Definitely it is a 1-1 function, because every element is associated with different elements or distinct elements of set B. So that is why it is said to be a 1-1 function, or rather you can say it's an injection. So now our interest is how many injections that can be formed. How many injections that can be formed? Very simple, very simple. I'll take like this. For x1, how many elements can be mapped? 5 elements can be mapped. For x2, because x1 is already mapping with one of these elements, x2 will not have 5 elements, but that will have only 4. So second operation can be performed in only 4 different ways. And if you come to x3, because x1, x2 are already mapping to any 2 elements of these 5, only 3 are remaining. So that is nothing but 3. So first operation 5, second operation 4, third operation 3. So it is nothing but 5 into 4 into 3, which is nothing but 5p3. So what we have derived, it will be clear now for you. It is what is the difference between n power r and what is the difference between n power r and npr is clear now. Previously we have derived it to be 5 cube, the number of functions, but 1-1 functions is 5p3. Understand? That means without repetition, it's nothing but number of 1-1 functions. So I can say this 5 is nothing but n of b and 3 is nothing but n of a. So number of 1-1 functions or injections is equal to n of b p n of a. N of b p n of a. So understand it, how the permutation is applied. Permutations is applied to find out the number of functions is this one. That is there the total number of arrangements. It is nothing but total number of functions. Their n power r, it is n of b whole power n of a. And the total number of arrangements of dissimilar things without repetition is npr we have derived, and it is n of bp n of a. It is nothing but 1-1 function. So now total number of many one functions. How do you understand this? Many one function is nothing but if at least two elements of set A, at least two elements of set A is mapping to the same element, then it is said to be many to one function. Many to one function, understand that all non-1-1 functions are many to one functions. What did I say? All non-1-1 functions are many to one functions. The total number of functions are these many. Total number of functions means what? Every function will be present in that one. Every function means one function is present, onto function is present, constant function is present. Every function, many to one function is present. Every function is present in n of b whole power n of a. Then what do we need? We need many one functions. Many one functions are nothing but non-1-1 functions. Non-1-1 functions means you subtract that n of b whole power n of a minus n of b p n of a. So, understand how this can be applied to the concept of functions. You might have understood this, the application of the same permutation and in the functions. So, not only this, you can derive the constant functions also. How many number of constant functions will be there? What is a constant function? Like constant function is in the form of fx equal to k. So, if you have same example x1, x2, x3, y1, y2, y3, y4, y5, let me say, then what is a constant function? x1, x2, x3. All the three elements should be mapping to only y1. And similarly, all the three elements can be mapped to only y2. All the three elements can be mapped to only y3. So, how many different types of constant functions you'll get? The number of elements in B. Number of elements in B is nothing but the number of constant functions. So, you can have the number of constant functions also from this one, that is number of constant functions is equal to n of b, understand, that is the number of elements in the codomain is nothing but a number of constant functions. Okay, so this is how we can relate this to find out the number of functions and number of one functions, number of many one functions, number of constant functions. Okay, now let us see the next one, like and dislike things. What does it mean? There are n things and R things are like things. N minus R things are distinct things. Distinct means what? Different. Distinct or different or same. Distinct things are there. So, totally how many things are there? N things are there. And what is the data here? Among N things, R things are like things and N minus R things are distinct things. Then in such a case, what should be the number of arrangements? Number of arrangements, always remember, like I'll explain you briefly the meaning of it. Mathematics is there. If you have mathematics, how many alphabets are here? 4, that's 4, 8 plus 3, 11 are there. And in fact, without any repetition or without any like things, they can be arranged in how many different ways? 11 factorial ways, or rather you can say it as 11p11 ways. 11p11 is nothing but 11 factorial ways. But what happens? You have 2 m's present here. You have 2 a's present here. You have 2 t's present here. Then when you rearrange them, what happens? If you write this m here and replace this m with this one, these m's are replaced. These m's are replaced or interchanged, I can say. Interchange. Is there any difference there? No. That means this 11 factorial will be more if you have this type of like things. This type of like things. Like things means if you take all the bananas are like things. Generally, in the nature, whatever is created by the God are all you can take them as different things. Whatever are created by the human, some are like and some are dislike. That means the things that are created by God are all to be treated as different things, and the things that are created by human are to be, some are like things and some are distinct things. So here in this case, whenever the repeated things or like things are there, then you have to count their number and you have to divide with their factorial, and simply I'll explain you like this. These are n things. Among n things, let us consider one permutation. Just go through the statement once. The number of permutations of n things taken all at a time, when p of them are alike and the rest all are different, is n factorial upon p factorial. That is the typing mistake there. That is not r factorial, that is p factorial. So n factorial upon p factorial, let me say. Now consider required number of permutations as x. Consider required number of permutations as x. What does it mean? The answer what we must get is nothing but x. Then in such a case, let me consider one permutation in them. In one permutation, how many things will be there? Because totally you have n things will be like this: x1, x2, x3, so on, xn things will be there. In this one, how many things are like things? P things are like things. That means somewhere here you will have p things like. Now I want to remove these p things from this one because they are like things, and I will fill those blank places. I'll fill those blank places with all different things, not only different among themselves but also different from the rest. That means all the n things are now different. If you replace p things, p like things, and if you fill those blank places with all different things, not only different among themselves but also different from the rest, then all the things will be different. That is, they can be now arranged in n factorial different ways. Now these p things among themselves can be arranged in how many different ways? P factorial different ways. Now understand, for one permutation, how many different permutations you are getting? P factorial different permutation you are getting for one permutation. But how many permutations are there? Totally x permutations are there. So for 1 it is p factorial, for 2 it is 2 into p factorial, for 3 it is 3 into p factorial, for x it is x into p factorial is equal to n factorial, implies x is equal to n factorial upon p factorial. So whenever you have the repetition of things or like things, then count the number and divide with that one. So the number of permutations of n different things, when p things are like things, then the number of arrangements will be n factorial upon p factorial. Okay, next, if p things, that's what is the next statement, is if p1 things are alike of one kind and p2 things are alike of second kind, p3 things are alike of third kind, and so on, then pk things are alike of kth kind, then they can be arranged in how many different ways? You can see that is p1 plus p2 plus p3 plus so on plus pk factorial whole divided by p1 factorial into p2 factorial into so on into pk factorial. Okay, so that's about whenever the like things are there, similar things are there, dissimilar things are there, then you can understand the thing. So to conclude, what is NPR? It is without repetition, dissimilar things, all things are dissimilar, and with repetition, all things are dissimilar. When p things are similar, then it is n factorial upon p factorial, and so many things are there, p1, p2, p3, so on, pk. These are all, this is first kind, this is second kind, this is third kind, this is kth kind. Then these can be arranged in how many different ways? Whole factorial, p1 plus p2 plus p3 plus so on plus pk factorial upon p1 factorial into p2 factorial into p3 factorial into pk factorial. This is the conclusion. Okay, now so go to the next slide. Next is a circular permutations. Before going through the circular permutations, let us work out, let us see the yesterday's doubt, that is fifth slide. Yesterday one girl asked this doubt, whenever 0 is included in getting the summation of different numbers formed, let us suppose 4-digit number formed from this one, then what should be the formula? So that you can see, that is that last class doubt is that one. Sum of all the r-digit numbers, please go through the slide. Sum of all the r-digit numbers formed by taking the given n digits including 0. Why I have taken including 0, you can understand now, is sum of all the n digits, that is add all these digits into n minus 1 p r minus 1. Here in this case, n is 6, r is 4, if you take 4-digit number, minus and so on into 1, 1, 1, so on, r times, minus p of n minus 2, r minus 2 into 1, 1, 1, so on, r minus 1 times. So n is 6, r is 4, so you make use of that formula directly and you can find out the sum of all the r-digit numbers formed by taking the given n digits. Okay, you can note down that formula. That is the yesterday's class. One girl asked that question, and you can understand this is n minus 1 p r minus 1 can be written using the formula n minus 1 factorial upon n minus r factorial. Okay, so that's why you can, we have already derived NPR. Using that, you can do this one. You can do this one. Okay. And one more thing, whenever you write some 7P3, don't totally apply the formula. Start from 7 and write consecutive 3 factors. 7 into 6 into 5. Similarly, 9P4 is there. Start from 9 and write 4 consecutive factors. Like this. Okay. So that's about this. Now, let us go through some problems. Please go to the slides. Find the number of arrangements that can be formed by taking all the letters of the word victory and find its rank if they are arranged in the form of a dictionary. So victory. How many letters are here? This is 3. This is 3, 6 plus 1, 7. Totally 7 letters are there. And you can observe that all these 7 are all different. So they can be arranged in how many different ways? 7p, 7 different ways, which is nothing but 7 factorial different ways. 7 factorial is nothing but, you can say it is 5040. It is 5040. So 5040 different letter arrangements you will get from the letters of the word victory. You can, in other way also you can think, how many letters are there? Totally 7. This is first, how many blank places we require? 7 blank places. 7 blank places. First blank place can be filled in 7 different ways. Second one 6. Third one 5, 4, 3, 2, 1. So which is nothing but 7 factorial using principle of counting, which is nothing but 7p7. We have just now derived the permutation formula. So the total number of different arrangements that can be got from victory are nothing but 5040. Now what is the question there? And find its rank if they are arranged in the form of a dictionary. And what is the arrangement of dictionary? You know, if you refer to the dictionary, the dictionary arrangement will be always, if you open the dictionary, first page consists of A, and if you want to see the meaning of some letter together, then how do you proceed? We will go to T. If you open the dictionary, you'll get A first, then B, then C, like that. If you go to T, then after T immediately you'll get A again. After A you'll get B again. But what we need? We need together. Together means TO. Then we'll go to O. And after O again, A starts. After A again, B. But what we need together. That is, our third letter is G. So we go to G. Like that, every alphabet in the dictionary will be arranged in the form of A to Z. The order is followed as A to Z. But in our dictionary, how many we have? 5040 different arrangements are there. Now these are to be arranged in the form of a dictionary, and if they are arranged in the form of a dictionary, then what should be the position of victory? Then you might be knowing the lengthy form of this rank. That is, if it is in the board, you will be working out. You might be knowing that. I'll teach you a shortcut here. Follow this carefully, please. And first of all, you give the alphabetical numbering to this alphabets. That is, first of all, you give the alphabetical numbering. Like what? If you see, C first comes. In the A to Z, what is the first letter? C. After C, I. C, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, Z. Just a moment. C, 1, 2, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, Z. You might be understood. You might be observed this, that I have given the alphabetical numbering to this one. Now, what you have to do, you have to count the number of digits that are less than each number only to the right side of it. You have to count the number of digits that are less than each number only to the right side of it. So let us count it. Less than 6 numbers. 1, 2, 3, 4, 5. So 5 are there. 7 is bigger than that. Less than 2, only 1 is there. Only 1 is there. And less than 1, only right hand side, please. Only right hand side. No other number less than 1 there. And less than 5, how many are there? 3, 4, 2 are there. Less than 3, nothing is there, 0. Less than 4, nothing is there. Less than 7, nothing is there. I repeat, whatever the word you take, first of all, give the alphabetical numbering according to A to Z. I have given that C1, I2, then O3, R4, and T5, V6, and Y7. Next, what I did? I have counted the number of numbers that are less than each number only to the right hand side of it. So less than 6, 1, 2, 3, 4, 5. 5 written. Less than 2, only 1. Less than 1, nothing is there, 0. Less than 5, 2 are there. Less than 3, nothing is there. Less than 4, nothing is there. Less than 7, nothing is there. Now you start from right hand side, writing from 0 factorial. 1 factorial, 2 factorial, 3 factorial, 4 factorial, 5 factorial, 6 factorial. Now multiply this. 0, multiply this. 0, multiply this. 0. This is multiply 3 into 2, 6, 6 into 2, 12, and 4 factorial into 0. It is 0. 5 factorial into 1. It is 120. You know, it is 5 into 6 factorial. 5 into 720. Add all this. That means these are the different arrangements before the victory, but there should be one arrangement for victory. So add 1 to this, then you will be getting 3733. This is the short form of finding the rank. Short form of finding the rank. So 0 factorial to 6 factorial and multiply together, and finally plus 1 is to be added, plus 1 for victory, plus 1 is to be added, and the final rank will be 3733. So for your homework, you just take down this and find out the practice rank, that is labor, mother, father, computer, and very interesting one is Chiru. What does it mean? Chiru doesn't require any arrangement here, because C is 1, H is 2, I is 3, 4, R is 4, U is 5. You can say 1 less than one number, nothing is there. Less than 2, nothing is there. Less than 3, nothing is there. Less than 4, nothing is there. Less than 5, nothing is there. So all will be 0, 0, 0, 0, 0. And 0 factorial, 1 factorial, 2 factorial, 3 factorial, 4 factorial. And if you multiply all this, you will be getting again zeros. But plus 1 for 0. So its rank is 1. Its rank is 1. Like that, if you practice this, you can understand this. And you may be thinking now, sir, if repetition of the letters is there, what should be done? That you have a previous question on that one, and the time is not sufficient to discuss that. We will discuss that in the next class, that is Cochin. It's 2008 or 2009 IIT previous question.